Yeah.
Tēnā koutou, tēnā koutou, tēnā koutou katoa. Nā mihi nui kia koutou katoa. No mai hara mai, whakatau mai kia tēnā rā. No mai hara mai ki te renga mātai pukaha. Ena mana, ena reo, rā rangatira mā. No reira, tēnā koutou. Ko Richard Clarke aho, he manakura te herenga mātai pukaha wa papatamata rau aho. Well, good evening, everyone. Warm greetings to you all. My name is Richard Clarke, and as the Dean of the Faculty, it's my very great pleasure to welcome you to this evening's inaugural lecture of Professor Oliver Sinnen. An inaugural lecture is a special occasion for the university which acknowledges the appointment or promotion of new professors. An inaugural lecture also gives the new professor a chance to demonstrate how their work is having a real impact on the world around us. A very special welcome also to our guests tonight. Just a few housekeeping items. If we do need to evacuate the building for whatever reason, please leave via the nearest exit and assemble on Simon Street. Bathrooms are located just outside the lecture hall here on the left as you leave, as you exit the door. And now would be a good chance to check that your mobile phone is turned off. It is now my great pleasure to introduce Professor Oliver Sinnen. Professor Sinnen graduated in electrical and computer engineering at RWTH Aachen University in Germany. He subsequently moved to Portugal, where he received his PhD from the Instituto Superior Técnico, IST, a University of Lisbon in Portugal in 2003. He has also been a visiting instructor and professor on several occasions at the École Normale Supérieure at Lyon in 2008, 2012 and 2015. Professor Sinnen's research lies in the area of parallel computing and programming with focus on scheduling algorithms for parallel systems. He leads a team at the University of Auckland which contributes to the development of the Square Kilometre Array radio telescope, and he also leads the Parallel and Reconfigurable Computing group here in the university. To date, he has produced over 100 peer-reviewed publications, brought in substantial external funding to support the work of his group, and has supervised close to 50 postgraduate students, including at least 12 PhD students, as well as 5 postdoctoral fellows, in addition to many more honours and intern research students. Professor Sinnen is also a committed academic citizen and currently serves as the Deputy Head Research in his department. Prior to that, he was the Programme Director for the Software Engineering Programme for a number of years and also led the accreditation of the Software Engineering Specialisation in 2015. Professor Sinnen is also a dedicated educator whose teaching is consistently well received by our students. He has received the Faculty Top Teacher Award on multiple separate occasions and also has been awarded teaching development grants both internally and from overseas funders, which are further testament to his commitment to our core purpose as a place of learning. And on top of that, he's also a really nice guy to boot. So, Oliver, it is with great pleasure that I invite you to give your inaugural lecture.
Thank you, Richard. Thank you. Thank you very much, Richard. Und ich heiße alle willkommen hier zu meiner Vorlesung. Ich freue mich sehr, dass ihr alle gekommen seid. And I didn't lose the plot. I just started in German, because I think that's quite fitting for the story. I want to tell a little bit how all this developed through the years. So, how did it all start? Actually, it started for me with this. So, should be doing something else. Hang on. Oh, so it started with this actually, and that was a quite interesting experience for me when I was in an arcade. At the age of maybe 10, 12, 11. It was difficult for me to access arcades. In Germany, they were normally together with gaming halls, and so we couldn't get in. We were with my parents in the Netherlands, and they left me there with a handful of coins so they could have a dinner without me. And I really was fascinated by this. So what I obviously wanted then is I wanted to, like many in my age, I wanted a gaming console. I got one, the Atari 2600, with a Pac-Man game. That was actually a bit underwhelming, that kind of game, but it's still inside really my desire to have computer games, and I wanted more of this. And so I got eventually, I think with 13, I got the Commodore 64, a home computer, 8-bit based, very slow in comparison to these days. But after playing the games, and that's where comes the story in now, I wanted to program them myself, right? So this here is kind of a simulator or an emulator of Commodore 64 as it was at the time. That's how it looked at the time. And this here is actually, and I recovered this, the first program I wrote with friends. So that was when we were 13, we wanted to program, we thought, oh, we can write games. So we started doing these kind of things. Not list run, I want to do a run first. It's a bit underwhelming, I have to say, after seeing this, but so we were 3 friends, we were in the basement, and we wrote something here, and we figured out how to use sprites, and we had a castle and the sprites, and the ghosts were flying in, and we were really proud of doing this, especially because we did this kind of in a night in the basement, and that was really fun. And what this looked like is such a program here. As you can see, this is just a basic listing, terrible code. You jump back and forwards. There's no indentation, nothing of what you normally would do these days. But it was too slow to program games, what we learned there. So it was kind of, we saw this code, we just saw the ghosts flying. And that was, in the basic programming language, actually the maximum speed of positioning the ghost one point to the other. So we didn't have the speed to write the games. We saw others, how others did this before. So I started actually with my friends, we learned assembly language, because that's kind of a very low-level language, how you program a CPU. But this was for us the only way of being able to write the software which we wanted. Not that we did any great game, it's just, but we were suddenly able to do the principle. We could write a breakout game, and that worked, but it was only possible to doing this. And so this incited, I think, my passion about writing optimized, very fast code, because it only was possible by having this kind of very fast and optimized code. And this is actually original code which I also lifted out from what I discovered from what we have written at the time. Very simple, didn't understand much, but we got what we needed to have there. Okay, so let's fast forward. After then finishing school, I went to RWTH Aachen University in Germany. It's very close to the Belgium and Netherlands. There is a bit of a point to why it's so close, or why I mention here that it's so close to Belgium and Netherlands, because while my wife, who's here, we have met actually at the university, but technically we met in the Netherlands in a nightclub there, because it was so close we could go to a nightclub in the Netherlands, and so that's where we have actually met. So a long time ago. I did start then also my international experience, and I went to a Trinity College in Ireland, Dublin, for half a year. And after this, so I finished then in my undergraduate degree with what was called a diploma thesis. And I wanted to do still something with optimization fast. I was a bit bored about the x86 world, so the normal processors that I used in most computers. And so I thought, okay, what's more fun to do parallel computing, and then more on a Linux, Unix systems, which are much more interesting. And so this resulted in writing a thesis in that domain. So from there on, and you might have guessed, the next step, because I went to Lisbon, my wife is Portuguese, so I had a very good motivation of going to Lisbon. I wanted to do my PhD overseas, and I found a very good supervisor in Lisbon at the Technical University of Lisbon, as it was called at the time. Now it's the University of Lisbon. It was a bit difficult to get admission there. The reason was what I had done in Germany wasn't really recognized in Portugal, so I had actually to do another master, if you consider what I've done before as a master. But I did this, I got a scholarship for my PhD, and I managed to do my PhD in Portugal then. Visited the Edinburgh Parallel Computing Center a few times in between, stayed there a few months, so maintained that desire to do international studies. So I finished then, or I did my PhD thesis, and that I think is quite clear now from the story I'm telling here, again in parallel computing, in a parallel computing topic. I did this in 2003, Richard mentioned this, and after that I came here to Auckland and joined the department. Okay, I told a little bit about how I came here and how this happened. But I haven't really mentioned what parallel computing actually means and why we are doing this and so forth. So, why parallel computing? Now, this is lifted from a slide I actually used sometimes or have used in a course I teach. And I write there multi-cores everywhere, so processes have multiple cores. Initially, I wrote PCs. Then, over the years, I added laptop. Then, over the years, I added tablets. Then, I crossed that out and put phones in, and I put smartwatches in. So now, these days, basically, everything that can compute is really kind of parallel. Supercomputers in the top 500 list. How many processors do you think has the fastest computer in the world? Any guess? Million. 10 million. 10 million you would have these days. Processors in the fastest computer. We have this everywhere. So parallel systems are ubiquitous. They are easily accessible. We can do this all, okay? So, but what's the benefit of a parallel system? Why would we use that? Okay, why is it interesting to think about this? So you get, of course, more responsive systems. You get shorter execution times. But I think that's just part of the benefit there. The biggest benefit which we see, we can tackle bigger, more complex tasks, new applications, new problems. And the computing power is, in a certain point of view, is arguably one of the biggest enabler in modern days in terms of technology. Machine learning advances, as we have recently, everybody is excited about, would be unthinkable without high-performance computing. The training of machine learning algorithms would be unthinkable without this. So this is absolutely instrumental, and it has led to many breakthroughs in the years in science and engineering and society. Is it gene sequencing, protein folding, training of neural networks, speech recognition, simulation, of course, or processing of large scientific data like in the LIGO or CERN, or, as I will later a little bit refer to, in large radio telescopes. Okay, so, I'm convinced, let's use computers. What's the problem? Okay, and now you come in. So I've given you all a number, okay, and I want to sort the numbers. So sort the numbers for me and bring them to the front of the, here to this desk. You have a number, sort them. You have to talk probably to somebody. Okay. this is actually an exercise I do in the class I teach in my Software Engineering 751 course for the students. And you might have guessed I want to experience that they experience and understand some of the problems of parallel computing. I have to admit they are a little bit faster than you guys. Obviously the problem is as an analogy, I consider you guys as processors, right? So each of you is a processor, each of you gets a data item, and you are supposed to work together. But what you of course have to think about is like, first, how do I give instructions? Now I voluntarily or like on purpose here, I didn't give you much instruction. That makes it a little bit more fun, right? But if I wanted to do this really, I mean, if I had given this to a single person, the single person had probably solved this much faster. Okay, so parallel computing, it wouldn't have much sense. So I have to decide how many people do I involve. Maybe 2 people would have been a better number. How many numbers do I give per person? 1 is probably a bad choice. Maybe I should give already 4, 5, 6, 8 numbers to a person. Which algorithm do I use? I mean, you might just put them there and insert things, right? That's called insertion sort. But from from sorting theory, there's plenty of algorithms. Some are better for parallelization, some are worse. I'm sure my students will know things like merge sort, quick sort, radix sort, and so forth. But the other point, of course, here comes in terms of how do you organize this? How do you communicate? Now, naturally, you do this by rows. Because you're sitting in rows, but if you designed a computing system, if you designed an architecture for this, how would you do this? How would you put the process? How would you connect them? So there's plenty of things that need to be decided, plenty of things that can be optimized and have a decisive influence on the efficiency of a parallel program. Okay, and that is really part of the research I'm doing, and there's many different aspects to it. So I will talk about 3 of those research topics, and here I start with the first one, task scheduling. So in task scheduling, and that becomes a bit abstract, and don't be afraid, I don't have much math in here, and I'm not going over it anyway. But so in task scheduling, what we do is we just represent a program, the input or the tasks as nodes here in my graph here, and I have to put them onto processors. This is a Gantt chart, as you would do, like maybe if you do management scheduling or any organization. This is time, this is process. I have to put them there, and there are so many problems of this that they even have a descriptive language here. I've just put this there. Never mind, but I want to find how I do put the task here so that the execution time is the shortest. Now, the interesting or the extremely fascinating aspect here is that this kind of problem is a so-called NP-hard problem. Never mind what that is. It's a term from complexity theory, but it means to get an optimal solution, to get the best possible solution, the execution time is exponential in the number of inputs. So the more with the number of tasks you have, with the size of the graph, the time grows exponentially. And there's not really anything you can do about this. So we need to find good solutions for practical approaches, for maybe not optimal approaches. And so that's what a good part of my research is about. The first part where I looked in particularly was the contention. So when you have say you have several processors and they execute something, and then there's contention. You would have had this in the way you're talking. If suddenly all people wanted to go to the corridor, you would have back off because the corridor is already full. There's contention for this. So you need to back off. Now, obviously, when you optimize something, you can do this in the best possible way. And this is thinking about this. Now, this actually led to a lot of research, and I was quite proud when I eventually wrote a book about this and published this, and that was really good, almost a business card whenever I came somewhere. People wouldn't know me, but they might have seen the book before. So that was really, really nice and really well appreciated in the community as also for me as in a career. But I stubbornly, even though it is difficult to find the optimal solution, sometimes I really stubbornly in my research I wanted to, but I don't care, I still want the optimal solution. So you can't escape the fact that it takes exponential time, that it takes a long time, but you can try to do this the best possible way. And a lot of research has gone in that, and that was funded with a Marston Award, and we have investigated a lot of things there, many different methodologies. We looked at state space search, integer linear programming, satisfiability model theories, and we looked at a lot of special cases. And so what I'm doing these days, and what is coming more and more important, is where there's not only a single objective, but there are multiple objectives. Where when you can't say, oh, I just have a program, I want to execute it as quickly as possible, but you want to save energy. You don't want to spend too much energy executing this. And why is this relevant? And we see this here a little bit on the diagram on the right. If you have the different kinds of memory accesses, if you have local SRAM, SRAM is the memory which is in the processor, or on-chip SRAM, which is a little bit, could be the cache, or you have the external memory, you have here the energy which you need for transferring one word. And you see there's orders of magnitude difference here. So having smart algorithms that try to locally compute things and not move data around will save energy. And that is clearly something we are working on and we are investigating at the moment and trying to see how much can we be fast and energy efficient at the same time. Okay, so this, of course, and I think that should be underlined in an inaugural lecture. It seems to be just about the person presenting, in this case, myself. But obviously, most of the research is done with teams or by PhD students. So I really want to acknowledge this. And I have listed here the PhD students that were integrated in this area and the collaborators here from the university that have done so. I think in terms of time, I will not have time to read them all out always. But I have them listed here, and I really acknowledge and appreciate the input I got and the collaboration and the teamwork we had. In terms of international research community, scheduling has a fantastic community, especially in Europe and in France and Germany. And I was really lucky to be able to go to France 3 times in 2008, 12, and 15, and being a visiting invited instructor there with a great team led by Yves Robert and later Frédéric Vivien. And that was really great, but there's also a lot of other collaboration I had with people in Grenoble, in Dortmund, in Göttingen, and even I had spent a month in Hawaii on a sabbatical. So not too bad. So that was really great research, and the scheduling community is great there. Okay, but this is just one aspect of my research, and that is kind of abstract theoretical, where you try to model something in an abstract form and you try to optimize it, but while you're doing it, you're not always looking back where this abstract form came from. A more practical approach was when we looked at how to program systems actually. Okay, so how would you write code? And many of you will have programmed, most of you will have programmed probably a bit in the context of writing maybe a script or a full program. And we want to, in this kind of research, we want to enable this kind of programming and make it easier and better for a very dominant programming language, Java, which is widely used, and we try to extend this in order to allow parallel computation, but by not being so low level as I described early on when I had as a child to go to assembly in order to get the performance, but having still the advantages of software engineering, but making this faster. And what we did, we basically used annotations, we used new keywords in the languages and did quite a bit with this. So I will have here a few people listed that did this, and I want to at least mention Mustafa Mirabi, my PhD student, because he tragically passed away very briefly after he had actually finished his PhD. And I thank you still, Richard, for enabling that you could graduate so quickly and before he passed away and before he wouldn't be able to go into the graduation stage. That was great. In terms of international community, our work was recognized, my and NASA's work was recognized by that we hosted a conference, a workshop on OpenMP. That's one of the standards we worked on and ported to Java. And that was in 2019, just before COVID hit. It was great for us to have that here, and it was a good feeling. Felt really well about this. I then embarked on another conference. I'm talking soon, but we weren't so lucky there. So, okay. So my last research area, just mindful of the time, is in I want to talk about is in reconfigurable computing. And that research area has to do with very special devices. So this is again going back more low level. So it's really low level, and it tries to use very specific chips that are called field programmable gate arrays. And in contrast to normal CPUs, in contrast to processors that can be freely programmed, these FPGAs, they provide a lot of flexibility. They can be highly parallel, but they are really, really difficult to program, or in other words, you have to go very low level to get good performance, and that takes a lot of effort. So our research in this area focused on methods, high-level synthesis methods. They focused on areas where you needed to find something to describe a complex algorithm, and then the underlying compiler and system and tools would translate it into the low level. And we applied this into several domains. We applied this into bioengineering applications, where we used this in order to have cell descriptions implemented in hardware. We used this for ray tracing. We used this for accelerating data structure that were embedded in hardware. And recently we do this now to implement machine learning algorithms on FPGAs. But we also use this, and that was mentioned before, for one specific area, which I think is maybe the most fascinating and interesting one in the context here of my research and what's used for FPGAs, and that was in radio astronomy. Okay, and I come to this in a moment. Here, just mentioning who I collaborated with. Again, this is inside the university, outside internationally, and a lot of postdocs and PhD students. I mentioned earlier we had here the technical, the FPT, the Field Programmable Technology Conference, where I was really keen and invite this and having this here, and we organized everything because, I mean, hosting it 2021 meant we started probably in 2019 organizing everything. We found venues, and then COVID hit, and we thought, okay, it's probably gone by 2021. We couldn't have been more wrong. So it was really the worst of both worlds, organized in person, but held virtually eventually. I was the general chair. Bruce Shem from the School of Computer Science was the vice chair. But it was still a very good and successful conference, and we were able to provide free registration and just having a few sponsors there. So that was a nice thing in this community. Okay, so I already said I was going to talk about a bit the pulsar search here, in reconfigurable computing. So pulsars, what are pulsars? And let me just start this here. So this is a pulsar, okay? The pulsar is a collapsed star. It's a neutron star. And that is something you wouldn't be able to see. It doesn't emit visible light. But it is highly dense. It's one of the densest objects in space. Only black holes are denser. It has a very small radius. It's only 10 kilometers, but has easily more masses than our own sun. And as you can see here, and that's the interesting part, it rotates around its axis. So you have something that's heavier than the sun, and it rotates around its axis in seconds. Okay, so Earth takes 24 hours. we have something that's heavier than the sun. It's like a intergalactic mixer, turns around. And because of all these qualities of all the density, it has a very strong magnetic field, electromagnetic field, as you can see here, symbolized by these lines. And as you can see, this electromagnetic field comes out at the poles. And that's the interesting part, because these kind of through the rotation and this electric field comes and hits the Earth. So whenever we see, basically we could detect this, because this electromagnetic field rotates, and then while it's doing it, if you're looking into that direction, we might be able to intercept this. Okay, so why is this interesting? Now it's interesting because it's extremely stable. Okay, it's just because it's gigantic. It rotates, and it rotates with a very constant speed. So sometimes these are described as interstellar GPS. If you know where a pulsar is, and you were flying with your spaceship in interstellar space, and you could always use a pulsar as your point of reference, because it really doesn't change in any meaningful way in a short period of time. So, okay, so pulsars have been detected, and people have basically that was in the 60s, and Nobel Prizes were awarded for detecting them. But what we are interested now more and more is to find not a single pulsar, to find binary systems. So where you have two of those objects, maybe two pulsars or a pulsar and a black hole, symbolized here on these images, where they rotate around each other. Why is this so interesting? Because you can detect the beam that comes around, and there will be tiny changes. And depending on those changes, you know something about the systems, and you can actually learn something about relativity and strong field physics. The problem is, binary systems are extremely difficult to detect, because the pulsar is moving in an orbit. And if it's moving in orbit, the frequency that emits a signal is altered due to Doppler effects. Okay? So that makes it very difficult. There have been detected a few ones, but we want more of them. The more we have, the more we can say about general relativity, we can more about strong field physics, but they can also be used as a very slow gravitational wave detector, when you have several of them. So we need a really good instrument to find them. And that's where this square kilometer array comes in. The square kilometer array is a radio telescope that's currently being built in sites in Australia and South Africa. It's going to be the world's largest radio telescope. It produces petabytes of data per day. So huge amounts of data are very done in real time. You need to process things in real time. There's no point of storing it, because you will never have the time to process the data later. Okay. So what are the challenges then to find pulsars? Now, we don't know where they are. We don't know the position. They're in the sky. We don't know how far they are away. We don't know what their rotation is, so the pulse period they send our pulse to us. And we don't know what their acceleration is. Okay? So, seems very difficult. Their signal that comes here is weaker than noise. So you need to integrate for a long period of time in order that the signal comes above noise. Okay, so the only way is brute forcing it. Guessing distances, guessing positions, guessing pulse periods, guessing accelerations, all kinds of them, and then computing, is there a signal? And if yes, we have found one, and we can verify this more precisely. Okay, so that's where our team came in. And we have done this here with a group of people here at the University of Auckland, but this was also in collaboration with people from AUT, Willem van Straten and Andrew Ensor. Both of them have now left AUT already due to their big restructuring. I was briefly during that time, part of the team in Manchester for the pulsar search. That's a photo of myself in front of the headquarters in Manchester, and the the large radio telescope they have there. And so what we did, we tried to implement algorithms to do this brute force search of the pulsar signal in FPGAs. Why FPGAs? Because they can be highly parallel, but they're also low power. And the signal comes in all the time. You need to be processing 24 hours. You process all the time. So you need to have a very good low power implementation that can do this in real time. Okay. And so we implement this using our high level methods, using this high-end devices. The design was quite complex. We needed to analyze, we had only basically 88 milliseconds before the next set of data comes in from the telescope. And then you have to do all this processing for all the possible acceleration distances and pulse periods and so forth again. And so we need to really analyze things, how to amplify signals, how to move data around, how to put things from one point to the other. And we ended up also needing to have really sophisticated ways of writing our code so that we could optimize it and find the best solution in an automatic way, so-called design space exploration, where we needed to find the hardware which we didn't know exactly what would be the best configuration, and trying out different ways of doing this. Okay, so that was really exciting and doing this for this kind of implementation or for this kind of application. Now, future challenges. Okay, so what comes next? What is the difficulty here in the next days? Okay, so I think at the moment is really power and energy consumption of computing. Here are a few examples just to illustrate what's happening at the moment. So GPT-3, that is the old version of GPT. I mean, it's not even 3.5 or GPT-4 or 4.0, which you have now been used to in the last years. Used 1,286 megawatt hours for training. And when they had 100 million users, it used daily 564 megawatt hours in energy. Okay. The first exaflop system, it's now the second fastest computer, Aurora in the United States, cost $500 million, not $500, there's a million missing, 500 million US dollars, and it has a power consumption of 40 megawatts. There's a new Microsoft data center being built in Germany, and I think in many other countries as well, and OpenAI thinks about even an order of magnitude bigger one, that costs 3.2 billion euros to build, and it will use hundreds of megawatts power consumption. So what we need to really think about how can we compute fast, maybe just fast enough, but in a much more energy and efficient way. And obviously there's many people working on it from a technology level. We will probably be looking at it from a more programming and scheduling level. And our focus is clearly on energy costs of data transfers. We do this, of course, with also with computing architectures for FPGAs on machine learning, energy efficient scheduling. I mentioned this before, and maybe looking at some ways of programming this. Just one simple example. I mean, programming something in Python will need more energy than programming the same algorithm in C. Okay, if you sort numbers, as we did, in different languages, it will have different energy consumptions. Also involved in the space research, being part of the Space Institute, and that I think that originates a little bit from simply the fact that I was so fascinated by radio astronomy that space has become a little bit passion, not only looking upwards, but now also looking downwards in terms of high performance computing in satellites and small devices. Okay. So I mentioned this before, that the title of professor in a certain sense belongs not only to the person receiving it, but also to all the PhD students, all the collaborators, all the undergraduate students that had actually built this. But not only that, there's also a lot of staff that supports us from a day-to-day basis. And I really want to acknowledge this because that's extremely important. So Emmanuel, Fang, Jamie, Sunita, James, Peter, and Rob. So that and that's just a few I mentioned here that supported myself and throughout the years, and that was really, really well appreciated. And administrative staff, it's the same. So Saida, Dennis, Claire Louise, Aruna, Chris, Linda, Jones, many of them have supported me, and really, I really appreciate this. Of course, all academics having a coffee chat with Nitish in the morning is very, but everybody in the department really, and obviously the head of departments, and I really thank Kevin for encouraging me also to apply becoming professor and supporting me in all the last years here. Okay, so, but obviously there's somebody I want to thank even more, and that's my family and my wonderful wife Patricia, my children Marvin and Liana. So I really appreciate very, very much that you have supported me and like we're bearing with my maybe my absence or moods sometimes. So really thank you for that. 20 years. I have been 20 years with the department. It's for multiple levels. Many things have come together in the last 2 months, really. So in August 2004, I joined the department. That's 20 years ago. I founded the PARC lab, the Parallel and Reconfigurable Computing Lab, where all this research happened. I became a professor, and last Monday, I became a New Zealand citizen. That's just taken off in the town hall on the stage. So this time I wasn't sitting happy clappy on the stage, but coming up to the stage and getting my citizenship. That was a long story as well. So I started this entire thing now with in German, coming from Germany, and now being a New Zealander, I think it's quite appropriate for me, and I feel comfortable to finish this presentation or this inaugural lecture with a karakia. Ki ora te marino, kia whakapapa pau namu te moana, hai hurahi ma tato I te rangi nei, aroa tu, aroa mai, tātu I, a tātu katoa, hui e, tāke e. Thank you.
Kia ora tātou. Hello, I'm Kevin Sowerby, and I'm the current head of the Department of Electrical, Computer and Software Engineering, but more importantly, I'm one of Oliver's colleagues and have been so for the full 20 years that you mentioned. So 20 years ago, you said it was August, right? we actually before that, we actually did some interviewing, and Oliver was one of the candidates. We also had Nirmal Nair and Valerie Viatkin, and I believe you all met together and were being interviewed, and you thought it was kind of like a death match.
Yeah.
Where there'd be just one winner. But it turned out we were very wise, and we actually appointed all three of you. So that was an excellent choice, I think, by the university. Also, 2004 was the first year of Catherine Watson, who's up the back there as well. So it really was a vintage year, I think. Yeah. And I actually had a look back through my emails, going back 20 years, the 200,000 odd of them. So, and I actually found one from you. I think it must have been your first email to the department.
Oh, really?
And it was on Friday the 13th of August in 2004 at 12:44 p.m. precisely. And it said, "Thanks for the warm welcome," right? And this was addressed to the whole department. So already back then, Oliver was demonstrating how he was most definitely a citizen of this department. So that was a great way to start. Back then, I think when you began, we were actually based in this building. I think it was. We were based up on level 7 and 8, and you would have had an office up there.
That's right.
Probably very briefly.
Yeah, very good.
Because almost immediately we moved out of this building and we went across the road to the science podium, right, which we called the podium, in the 300 block. Can you remember what your office number was over there?
I don't
You're
know.
good with numbers.
Good memory.
I think it was 303156. Does it sound familiar? Anyway.
Probably, yeah.
And we used to have all our labs down here, down on level 3 of this building. We're on level 4 down. We had some. There used to be a building where the building 405 now stands. There were some labs up there. We used to call them the junior and senior lab. We taught them, but we shifted everything across to the science podium. And that was actually quite a transformation for the department that you were part of, most certainly, because suddenly the technicians were together with the academics and the administrators, and we really did become one big family. So that was important to us. And you were there. And I have to say, when Oliver started, I guess you were meeting lots of new people and you sort of be overwhelmed. And so I was there in 2004 when you began. In 2005, I was away. I came back, it was a research and study leave. I came back in the beginning of 2006. Now, back in those days, Oliver had no children, right? And I had no children. And we had time to spend on ourselves, so we actually used to go to the gym a lot, right? A gym which is also no longer there. It was demolished to make way for a new one, and so we would be there probably every second day or so. And I can remember, as you do in a gym, you sort of say hello to people in the changing rooms, and then you're off, and you may not even know exactly who they are. But then one day, we were back in the department, and Oliver met me. And he sort of looked at me curiously, and then there was like this flash of recognition. He said, "Oh, Kevin, I didn't recognise you with your clothes on." So that's something I remember from way back then. And I kind of knew at that moment perhaps all my misconceptions about Germanic sense of humour should go out the window. And I knew it'd get on from that point. So you've told us a lot about the work that you've been doing, right? And it's interesting when in your field you deal with time of like milliseconds, microseconds, nanoseconds, so you understand those very well. But what impresses me is that that's a sort of an electrical network point of view. But from a social point of view, and the networks that we build as humans, you understand what years and decades mean. And you have spent the last 2 decades building up your network with your colleagues, your network with your collaborators, with your students, with the postdocs. And that's been wonderful to see what's come of that. And of course, we're still only, halfway through, so there's lots more to come. I'd also like to acknowledge Oliver's family who are here, because you can never do these things alone, and I know that Oliver receives lots of support from you. We greatly appreciate that. I'm sure you are celebrating his achievements today, and you are also to be celebrated for contributing to those achievements and supporting Oliver. And I'll also point out we should thank the German government for finally allowing Oliver to become a New Zealand citizen. He has been trying for some time. Apparently the German government did not allow dual citizenship unless you were kind of a special case. And Oliver's a special case, and so they actually allowed him to become a dual citizen. But then I think they've just changed the rules recently.
In July.
So anybody can do it. But however, you are now a citizen, so congratulations on that front. Now, just before we go out, and we're going to have some refreshments later, and we'll just after this, and we can go out and congratulate Oliver. We can sort of enjoy each other's company. But before we do that, we have a tradition in the faculty where we present the new professor, in recognition of all their achievements, with a book, right? And this book is actually their own work, right? So inside this book, we have lots of papers, lots of words and numbers and graphs, all the stuff that Oliver will understand because he wrote it. But this book is more than just a collection of papers. This is recognition of 20 more years of work, right? And it's 20 years of networking, it's 20 years of dealing with colleagues and students. So every time you look at one of these papers, you will think about them, you will think about the times that went in, as well as the intellectual effort and the contributions that you've made. So take this book, you can put it up on your bookshelf, but take it down occasionally and remember what got you here. So Professor Oliver Sinnen, congratulations.
Thank you. Thank you.
And so now I think it's time we can move outside where there should be some refreshments for us.